Hey, I'm Max, and this is the final video for the project. So our objective is to monitor 9 feline species, including the Siberian tiger, the Arabian leopard, and the Iberian lynx. We plan to use a space-based system to track these cats within a 2.5-mile radius, and each satellite in the system is not going to cost more than $750,000, and the whole system should cost less than $35 million. So for our mission concept, we plan to use a Walker Delta constellation to have complete coverage over regions in Asia, Africa, Europe, and the Americas. And we plan to launch these satellites into LEO at Cape Canaveral launch site. For our launch vehicle, we plan to use the Falcon 9 from SpaceX because it's cheap for small satellites, and they also have a near monopoly on this market, so they're the only option really. And each launch is going to cost around $0.35 million for each satellite. And again, we are launching from Cape Canaveral because it's better for non-polar orbits. So for our actual satellite, we chose an EnduroSat CubeSat to give us a lot of options for customizations and its lower price. And we chose the 6U size due to it weighing less and being less expensive. The total mass is predicted to be around 16 kilograms, and we plan to use both optical and infrared sensors so that we can make sure we spot our targets. We are going to have around $140,000 left to purchase our sensors. We thought about using SAR, but we decided against it because it would drastically increase price, and we would be past 100 million by now. So here are some additional satellite components. We have a UHF transceiver and X-band commercial antenna for high-speed and stable communication. And then we also need some solar panels so that we can generate power for the satellite. And then there's the other components there. And all this is gonna come out to around $125,000. So these are our optics calculations. So we assumed a nadir angle of 25 degrees. That angle determines how wide our viewing area is and how far our satellite can turn around and stuff. These numbers are a little clearer. So we have an entire axis area of 10 to the 9th square kilometers, and everything we can actually see is going to be 170,000 kilometers squared. And our entire axis area is going to be, that's basically how far we can see theoretically. Far sensors didn't have the limits they do. So this is our ground resolution. So at any given point in time, we can access 240 square kilometers. We're going to have 120 million pixels in the total swath. So the resolution is going to come out to 2 square meters per pixel, which is pretty good to see these cats. So for our constellation and network, we are going to use Amazon Web Services Network. And our satellites are going to have a maximum access gap of 18 hours. So at most, every 18 hours they will communicate with the ground stations. We plan to use a delta constellation with an inclination of 65 degrees. We're going to have 70 satellites in 10 planes. This is going to maximize our coverage as opposed to a Walker constellation, which wastes a lot of coverage in the upper and lower latitudes. So we have all our satellites are constrained with direct sunlight, so they can only, in this STK scenario, they can only see our specified areas during direct sunlight. So we make sure we can always see them. We have a 93.7 satisfaction for our 12-hour maximum revisit time. So we're going to be able to see our targets every 12 hours, the most of the time shorter. And this is going to come out to $52.5 million. We are 50% over budget, but we just weren't going to be able to do it with the 35 million we were allocated originally. So this is what we came out to, and we think it would be worth it. So for power, we have a max continuous, our power module is going to have a max continuous power of 437 watts and 75 watts of peak input per channel. And we are going to have solar panels that generate around 20 watts in Leo. So our payload is going to take around 10 to 30 watts. So here are our calculations. So the degradation of the satellite is going to be mostly negligible since this mission is quite short. And at the end of life, we're going to need about the same amount of power, about 105 watts per meter squared. And the solar array will be able to provide 172.5 watts. And so that comes out to an area of almost 2.5 square meters to provide enough power for all the systems on board. So here is our thermal portion. So our satellite, we think, is going to be able to handle between negative 35 degrees C and 75 degrees C. So we plan to make the structures from aluminum, and that's going to be better for dissipating heat and be cheaper. And we plan to cover the satellite in Teflon tape so we can increase the emissivity and lower the temperature. So here are our thermal calculations. We have an absorptivity of 0.14 and emissivity of 0.75. These are general values for the Teflon tape. And in the worst sunlit case, this is the hottest it'll get. It'll come out to 53.8 degrees Celsius. So we're still far below our threshold. And in the worst eclipse case, this is the coldest this thing is going to get. It's going to be negative 0.2 degrees Celsius. That's far above our coldest threshold. So here is our link budget. We are using a link budget margin of 1 decibel, so the constellation has reliable communication with Earth. And we have 200 megabits per second for fast communication and between the constellation and our ground network. And then, yeah, here are our sources. Thank you.